Here we go, last section of Chemistry 20 and Chapter 8 for you all. What we're talking about here is something known as titration, and titration is really just applied solution stoichiometry. Titration is the name of the entire process of adding one solution to another solution. What makes this special is that you have a highly calibrated device here known as a burette, so you can read it with amazing precision on volume, and your sample is done using a pipette, which we've used earlier, which is again a very precise way of measuring volume. So in other words, a titration is a very precise solution-to-solution stoichiometry problem. It's got a few different terms within it that we need to know and become familiar with. And so titration is really just the careful and controlled addition of one solution, all right, called the titrant, from that burette, which is really just a very long, slender, graduated cylinder that allows us to measure added volumes very accurately. So your titrant always exists in the burette, okay? And with your titrant, what's important to realize here is that this is the measured volume. Okay, so that's the measurement that we're trying to get out of this one. The other solution in the problem is known as the sample. And the sample is a precisely fixed and known volume of your second solution. All right? This is the one that is in limited supply. It is your fixed quantity and therefore usually plays the role of the limiting reagent. And so your sample hangs out down here. All right, it is a fixed volume as determined with a pipette. Okay, so remember those pipettes that, maybe you don't remember those pipettes that you were using because we did Chapter 5 from home. All right, so I'll talk more about pipettes here in a little bit, but a pipette is just another way of measuring very, very precise volumes. All right, so what we're going to do is we are going to take an initial reading from our burette, that's our starting volume. We are going to slowly add this titrant to the sample. We'll start to see flashes of a new color and things like that within here because the indicator that we have used is starting to show its nature due to pH changes. And then we'll get to a point known as the end point when you get that permanent color change. So we'll get that permanent color change, and we will stop adding this titrant and we will take a final reading. The difference in initial and final readings is the volume added, and we measure this as precisely as possible, and we've got a couple examples on the later pages here to show you exactly what I mean by that. Okay, so that in a nutshell is titration, adding one solution to another solution in which one volume is variable and the other volume is fixed. This one is fixed to behave as the limiting reagent, and so you're trying to figure out a minimum amount of excess reagent required to neutralize it and change the color. Okay, so this endpoint that you measure and see is the observed qualitative change. Remember, at the beginning of this chapter, we talked about qualitative chemistry and using color and certain things to identify changes in chemical state and reaction. So this one, the endpoint is when that sudden color change is observed. What we can do with stoichiometry is look for the equivalence point, which is the stoichiometrically perfect mole-to-mole neutralization. Obviously, we can't find this experimentally. We don't have the ability to put in the perfect exact number of molecules required to have a perfect neutralization or reaction. So what we do is we look for a measured endpoint that is as close as possible to the equivalence point that we can get. Usually, this is looked at as a one-drop difference between the two. Okay, I should be able to control this titration well enough that I'm within 1 drop out of the burette within that perfect mole-to-mole neutralization. Okay? Titration error is essentially the distance or difference between equivalence point and end point. If I take too long to turn off my burette when I see that permanent color change, then I'm going to be quite a ways away from any sort of equivalence point or stoichiometrically predicted value. So, our common sources of error here is overshoot, adding too much. All right. So what we'll do to minimize this is we will typically do multiple trials. And what we do is we say when you get to 3 consistent results that are no more different than plus or minus 0.1 mils, you now have a successful titration. Because we're not in lab doing this and we're not getting a chance to work with this, it's a little bit tough to do titrations in a vacuum or just theoretically here. So a couple things that I want you guys to do. Watch this video a lot. Okay, it's about 4 minutes long, and it's going to take you through how to perform these titrations and what we mean by equivalence and endpoint, titrant and sample and pipetting and all of those things. Okay, you will find all of these in the chapter 8 or in the video section in content. In D2L. Okay, so where I've sent you for other videos, you'll find those there as well. It is ultimately important that you watch these ones so that when we're doing titrations in Chemistry 30, all right, you have a better chance of being able to perform them and understand them well. Okay. Now the rest of this, when we take a look at doing titrations on paper, it is pretty much identical to everything we've already done with Chapter 7, limiting and excess reagents, and making predictions based upon stoichiometry. The difference here is we have some sort of measured quantities, so pay close attention to the difference between example number 1 and example number 2. Number 1 is the way we looked at it in Chapter 7. We have a known limiting reagent, you can see from the information given, that we're asked to figure out how much of this is needed to completely consume HNO3. So it's just a one-step stoichiometry problem. I'm going to start with my concentration because it does put moles in a good spot. 0.35 moles per liter of HNO3. All right, I will cancel out the volume here. All right, by multiplying through 25 mils. I now have millimoles of HNO3. If you don't like that, you could have stayed in liters, it's fine. And since I have a mole quantity, I can now do my prediction. And you can see in the balanced equation, it's 1 part NaOH for every 1 part HNO3. HNO3 now goes, and I have millimoles of sodium hydroxide. I just need to cancel out the moles and get to liters, and so I can use my concentration here of 0.15 moles per liter. Moles now go, and I have milliliters of NaOH. Run that through your calculator, and you get 58 milliliters when you round to your 2-digit limit. Okay, and that's the stoichiometry that we've seen before. That's the stuff that we remember, and it should be no problems going from solution to solution. Here's the difference mathematically for a titration. You'll see this big ugly table of data. And when you take a look at this big ugly table of data, you'll be thinking, what am I doing? Well, here is all of your individual trials. You have final and initial readings of the HCl that you are adding. So that must mean, since I'm adding HCl, that is my titrant. And so this is the one that I have to measure and hopefully come up with 3 good trials. If HCl is my titrant, then this is my sample, and it's the one that's sitting in the beaker or the flask underneath your burette. So before we can start filling out all of our data, maybe actually what we can do is we can interpret this title first, and you can see that you have 20 mils of NaOH. You'll notice all the extra decimal 00s. That means it was measured very precisely with a pipette, and so you're getting more significant digits. You're also titrating this with 0.250 mole per liter HCl, so I have this. We're being asked to determine the concentration of NaOH, so this is what we're looking for. And so we just need one other thing. We need a volume of HCl. And you can see that we have added HCl 4 times. What we're looking for here is a best average volume. All right, the way to minimize error in a titration is to do multiple trials until you get 3 consistent results. So what we would do is we would take the difference between initial and final in all of these trials and figure out how much was ultimately added. In the first trial, we added 47.50 milliliters of HCl. In the second, 46.50. In the third, 46.60. And in the fourth, 46.50. When you take a look at these ones, remember we said plus or minus 0.1 mil. 47 to 46 is a 1 milliliter difference, but 46.5, 46.6, and 46.5 are all within 0.1 mils of each other. So that means the first trial was likely just a quick overshoot, and you'll see that in the video I've asked you to watch. And he was able, or the experimenter, the student here, was able to get the next 3 trials to be good. And so we just take the best average volume of these 3, which is 46.533 repeating milliliters. So now I have a volume that I can now use. So the data table was only there to get a volume of titrant so that I had enough information to be able to do stoich like I did up here. All right, so now it's just quickly running through the calculation. I'll start with my concentration again, 0.250 moles per liter, times the best average volume here of 46.533 milliliters. The liter goes. I now have millimoles. I can compare it to the balanced equation, and oops, I forgot my HCl. Okay, and so I take a look at HCl versus NaOH. They're both 1 part each. HCl goes. I now have millimoles of NaOH, but I wanted a concentration, so I'll put the volume of it in the denominator here. And you can see the milli now goes, and I have moles per liter of NaOH. Run that through your calculator and round it to 3 digits, and we get 0.582 moles per liter for my NaOH. Okay, there you go with that one. You can see it's the same stoichiometry. Don't let the data table mess you up. The title is always descriptive. It tells you what titrant and sample are. Specifically measured volumes of the sample. Whatever you're adding is your titrant. So the best average volume goes with that titrant. And then once you've got that information complete, it's the same stoich you know and love. There you go, guys. Next 2 examples in the following video.